Swayam Prabha. Digital India. Educated India.
I welcome you all to lecture number 10 in which we will be dealing with gas turbine cycle, that is the Brayton cycle. So, let us have a quick recap of what we have discussed in the previous lectures, especially lecture number 7, 8 and 9. So, we have started the module number 2 in lecture number 7 with the air standard cycle, especially we focused on Otto cycle, which is the cycle on which a petrol engine works, a spark ignition engine works. Then we have seen the diesel cycle on which a diesel engine works. Of course, all the cycles which we have discussed are ideal cycles. There are a few assumptions that has been made in the ideal cycle. There are deviations of ideal cycle from the actual cycle. Then we have seen the dual combustion cycle in the previous session, previous lecture. That is, the heat addition is a combination of constant volume and constant pressure, whereas the heat rejection is at constant volume process. So, in all the three cycles before, we have derived the thermal efficiency or the air standard efficiency. We have introduced the ratios like compression ratio, cutoff ratio and pressure ratio. Compression ratio is there only for the Otto cycle, cutoff ratio is there for in diesel cycle as well as the compression ratio, and in the dual combustion cycle we have got compression ratio, cutoff ratio and pressure ratio. So, now let us see the construction and the working principle of a Brayton cycle. The contents of my presentation for today's lecture is ideal cycle. We will see the ideal cycle, the pressure volume and the temperature entropy diagram of a Brayton cycle, various processes, derivation of thermal efficiency, how the actual cycle deviates from the ideal cycle, and a few numerical questions. So, this is the construction of a ideal Brayton cycle. So, when we talk about Brayton cycle, actually there are two cycles, one is a closed cycle, another one is a open cycle. So, the schematic which is shown now, it is a closed system, it is a closed cycle. There are four major components: compressor, heat exchanger, two heat exchangers and turbine. So, let me explain this the ideal cycle first. Here air is admitted into the compressor. The air from the atmosphere is taken at state point 1 where it is compressed to high pressure and high temperature, and it leaves the compressor at state point 2 and goes to a heat exchanger. Before seeing the ideal cycle, let me tell what is the difference between the actual cycle and the ideal cycle, so that it will be easy for the students to have better clarity. In case of an actual cycle, what happens is there are only three devices, major components, that is compressor, combustion chamber and turbine. There is no heat exchanger which is located at the bottom portion in the schematic which is shown. So, the air is compressed to high pressure and high temperature, then it is in the combustion chamber, the fuel is sprayed, the combustion takes place, the products of combustion are expanded in a turbine, and it is let out to the atmosphere, because it is an open cycle in case of a actual cycle. In the ideal cycle, the modifications done are, we have two heat exchangers. One is for heat addition, another is for heat rejection. One is for heat addition and another is for heat rejection. So, the combustion process is replaced by a heat addition process which is done in the heat exchanger which is at the top, and the exhaust process is replaced by a heat rejection process. So, like diesel cycle or Otto cycle, where there also the combustion process is replaced by either a constant volume heat addition process in case of a Otto cycle, or a constant pressure heat addition process in case of a diesel cycle. In both the cycles, the exhaust process is replaced by a constant volume heat rejection process. So, similar to those cycles, here also the modifications have been done in case of an ideal cycle, where the combustion process is replaced by a constant pressure heat addition process. We will see the various processes, the PV diagram and TS diagram in the subsequent slide, and the exhaust process is replaced by a heat rejection process. So, here the power which is the power produced by the turbine, it is due to the expansion of the hot combustion gases, high pressure to the ambient pressure, atmospheric pressure. Mostly in an open cycle, it is the gases after expansion, or the gases are let out to the atmosphere. It is not recirculated again in case of open system, open cycle gas turbine, Brayton cycle. This is a closed, so and also it is an ideal cycle. So, the working fluid is considered as the air, like how we considered in Otto cycle, diesel cycle and dual combustion cycle. So, after expansion, the working fluid is cooled in the heat exchanger, which is located at the bottom portion, where the heat is rejected to the sink, and again the working fluid is circulated, where it is compressed to high pressure and high temperature. Then constant pressure heat addition process takes place. Then the combustion, then the expansion process takes place in the turbine. Instead of the combustion process only, we have the constant pressure heat addition. Then after expansion, we have the constant pressure heat rejection. Again the cycle is repeated, continuous. So, if you see there is a connection between the compressor and the turbine, The power required to drive the compressor is taken from the turbine itself. Whatever the turbine is producing output, the output power, portion of the power, electrical energy, is used to drive the compressor. So, the net work done during the cycle will be turbine work minus compressor work, So, this is, we will see in the subsequent slide in the derivation. So, this is the pressure volume diagram and the temperature entropy diagram of a Brayton cycle. Let me draw and explain the process so that it is easy, you can easily understand. So, first let me draw the PV diagram on the left side, and on the right side I have the temperature entropy diagram. Okay. So, process 1 to 2 is isentropic compression. So, as usual there is no change, this one, the 1 to 2 is isentropic compression. It is a vertical line on a TS diagram, 1 to 2, where entropy at 1 is equal to entropy at 2, temperature T1 in temperature at 2 is greater than 1, T2 is greater than T1. So, this is an isentropic compression process on a temperature entropy plot, and on a pressure. Okay, so, this is reversible adiabatic compression process, where the pressure increases from P1 to P2. The pressure of the working fluid and the temperature of the working fluid is raised during the compression process. Okay, so, this is the volume at 1 and volume at 2. V2 is less than V1. So, process 1 to 2 is isentropic compression. Next one is heat addition process. In case of a ideal Brayton cycle, the heat addition process takes place at constant pressure. So, y-axis is the pressure line on the PV diagram. So, this is 2 to 3. Line should be perpendicular to y-axis or parallel to x-axis. And here I will plot like this. This is a constant pressure heat addition process. Qs is the amount of heat supplied. So, let me plot here also Qs. Okay. So, process 2 to 3, this is point number 3. So, the pressure at 2 is equal to pressure at 3, because 2 to 3 is constant pressure. So, I can write like this, P3 is equal to P2, and the peak temperature or the maximum temperature occurs at point number 3. this is the maximum temperature that has occurred, and the maximum pressure occurs at point number 2, which is equal to P2 equal to P3. So, this is the end of heat addition process. Now, expansion, reversible adiabatic expansion. So, similar to process 1 to 2, where entropy is constant, S3 is equal to S4, S3 is equal to S4. And here the trend of the curve will be similar to 1 to 2. So, let me redraw it. Three to 4. So, 3 to 4 is isentropic expansion of the products of combustion. The hot gases which are produced during the constant pressure heat addition process are expanded in the turbine, where the pressure and temperature of the working fluid drops. And 4 to 1 is constant pressure heat rejection, So, again a process 4 to 1 and 2 to 3 on a PV diagram will be a similar curve, only the direction, the direction in which the arrow marks are marked are different. So, this is, let me write 4 here, this is 4, and here it will be similar to this curve 2 to 3. So, this is 4 to 1, heat rejection process QR. Let me use the same notation, like QS is the amount of heat supplied during the heat addition process, QR is the amount of heat rejected during the heat rejection process. Like Otto cycle and diesel cycle, Brayton cycle also has 4 processes. Only in dual combustion cycle there are 5 processes. So, let me emphasize that once again. So, this completes the thermodynamic cycle. So, process 1 to 2 is isentropic compression, 2 to 3 is constant pressure heat addition, 3 to 4 is isentropic expansion, and 4 to 1 is constant pressure heat rejection. And P2 equal to P3, pressure at 4 is equal to pressure at 1, pressure at 4 is equal to pressure at 1. So, this is V1, this is V4, pressure at 4 is equal to pressure at 1, because there are 2 constant pressure process, both heat addition as well as heat rejection in an ideal Brayton cycle takes place at constant pressure, If you recollect the process in the previous air standard cycle which you have discussed, Otto cycle, both heat addition and heat rejection is at constant volume. So, it is Otto cycle is also called as constant volume process, both heat addition and heat rejection takes place at constant volume. In Brayton cycle, both the heat addition process and heat rejection process takes place at constant pressure. In case of diesel cycle, heat addition is at constant pressure, whereas heat rejection is at constant volume. In case of dual combustion cycle, heat addition is partly at constant volume, then constant pressure, whereas heat rejection is at constant volume. So, in all the previous 3 cycles, the heat rejection takes place at constant volume, whereas in case of a Brayton cycle, ideal Brayton cycle, the heat rejection takes place at constant pressure. So, these are all the differences in terms of processes if you compare all the 4 air standard cycles. So, let me derive the air standard efficiency of the ideal Brayton cycle. So, this derivation is it is simpler one like the Otto cycle. It is not as lengthier as the thermal efficiency of a diesel cycle or a dual combustion cycle. So, let me define the efficiency. This is W net divided by heat supplied QS. Okay. See, if you look at this diagram, here heat supplied minus heat rejected, because this is an ideal cycle. So, the net work done is the heat supplied minus heat rejected, but in case of the actual this one, the net heat, the net work done during the cycle is turbine work minus compressor work, turbine work minus compressor work. So, this is equal to net work done is heat supplied minus heat rejected divided by heat supplied. So, like before, divide the numerator by denominator, Qs by Qs is 1, 1 minus Qr divided by Qs. So, this will be equation number 1. Equation number 1. Let us define the ratios before that. Rp is the pressure ratio, which P2 by P1. That is, if you see pressure ratio, this is this pressure by this one. So, Rp is the pressure ratio P2 by P1. Pressure of the working fluid after compression to the pressure of the working fluid before compression. So, that is P2 by P1. I am defining the term pressure ratio. So, Rp is equal to P2 by P1. This is the pressure ratio. If you look at the PV diagram, P2 is equal to P3, pressure at 2 is equal to pressure at 3, and similarly pressure at 2, this is point number 1, pressure at 1 is equal to pressure at 4. So, this can be modified, P2 is equal to P3 and P1 is equal to P4. Okay. Now, let us write the equations for heat supplied and heat rejected. Heat supplied is, let me draw the TS diagram just for better understanding. So, this is the TS diagram 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So, during this process 2 to 3 heat is supplied and during this process 4 to 1 heat is rejected. Okay. So, this is T2, this is T1 and this is the highest temperature. So, let me draw this again. And this is the highest temperature T3, the peak temperature that occurs in the cycle. So, 2 to 3 and 4 to 1 are constant pressure. So, here pressure is constant, here also pressure is equal to constant. Now, the heat is supplied during process 2 to 3, constant pressure process. So, assuming 1 kg of the working fluid, so constant pressure is Cp into delta T. Delta T, the process, the heat addition process starts at 2 and it ends at 3. So, the highest temperature is 3 T3, the lowest temperature is T2. So, T3 minus delta T is T3 minus T2. Similarly, let us write the formula for heat rejection process. Heat rejection process is taking place during the process 4 to 1. So, T4 minus T1. Here also Cp, because both the heat addition and heat rejection are constant pressure process. So, we have to use Cp and not Cv. So, this is Cp into T4 minus T1. The heat rejection commences at state point 4 and it gets over at state point 1. Now, let this be equation number 2 and this be equation number 3. Equation number 2 and equation number 3. Substitute 2 and 3 in 1. Substitute 2 and 3 in equation number 1. So, we get the thermal efficiency is equal, let me write it here, 1 minus Qr, instead of Qr I will substitute Cp into T4 minus T1, instead of Qs I will substitute Cp into T3 minus T2. So, you have to substitute the equation number 3 in the numerator and equation number 2 in the denominator. So, Cp and Cp will get cancelled. So, we will get 1 minus T4 minus T1 divided by T3 minus T2. So, let this be equation number 4. So, we have to express T2 in terms of T1 or T1 in terms of T2, similarly T3 in terms of T4 or T4 in terms of T3, like similar to Otto cycle. So that the temperature terms will get cancelled and we will get the air standard efficiency or the thermal efficiency in terms of here in this case pressure ratio, gamma, etc. Okay. So, now let us add one more this one. If you see this is what 1 minus T4 minus T1 divided by T3 minus T2. T3 minus T2. Okay. So, now let us, so consider the process 1 to 2, consider the process 1 to 2. 1 to 2 is isentropic compression of the working fluid. So, I can write the relation between temperature and pressure. T2 by T1 is equal to P2 by P1, P2 by P1 whole power gamma minus 1 by gamma. Let me recollect some of the basics here. If you are writing the relationship between temperature and volume, for example T2 by T1 means right side it will be V1 by V2. It is, if it is temperature is 2, volume is 1. If the denominator we are writing T1, that will be volume will be V2. But whereas if you are writing the relation between temperature and pressure, if you are writing the relation between temperature and pressure, here it is 2 means here also it is 2, here it is T1 means here it is P1, here it is P1. Now this P2 by P1 is nothing but pressure ratio Rp, pressure ratio Rp. So P2 by P1 is pressure ratio Rp. So that is what I have substituted here. From this we can find therefore T2 is equal to product of T1 into pressure ratio to the power of gamma minus 1 by gamma. Let this be equation number 4, equation number 5, equation number 5. So this is T2 in terms of T1. So here I have expressed a T2 in terms of T1. We can do the vice versa also. T1 also can be expressed in terms of T2. Next I will express either T3 in terms of T4 or T4 in terms of T3. So for that I am considering the process 3 to 4, 3 to 4. Consider the process 3 to 4. Again 3 to 4 is reversible adiabatic expansion of the working fluid, that is isentropic process. So let me write T3 by T4 is equal to, if it is T3 the pressure will be P3, if it is T4 the pressure will be P4 whole power gamma minus 1 by gamma. Now what is P3? P3 is P2. If you look at this diagram, P3 is equal to P2 and P4 is equal to P1, because 2 to 3 and 4 to 1 are constant pressure process. So P3 is equal to P2, P4 is equal to P1, and the ratio P2 by P1 is nothing but the pressure ratio Rp. So gamma minus 1 by gamma whole power gamma minus 1 by gamma. Therefore T3 is equal to T4 into pressure ratio power gamma minus 1 by gamma. So this will be equation number 6. This will be equation number 6. Now subs 2 is in terms of T1, T2 is in terms of T1 and T3 in terms of T4, T3 in terms of T4. Substitute 5 and 6 in 4. Substitute equation 5 and equation 6 in 4. So what is equation number 4? 1 minus T4 minus T1 divided by T3 minus T2. 1 minus
T4 minus T1. Let me rewrite the equation number 4 again, T3 minus T2. So, 1 minus numerator I am going to keep as it is, because we have found a T2 and T3 which are in the denominator. So, there is no change in the numerator, divided by, instead of T3, T4 into Rp power gamma minus 1 by gamma. So, this is, let me put one bracket here, minus, instead of T2, T1 into Rp power gamma minus 1 by gamma. So, in the denominator we can take pressure ratio to the power of gamma minus 1 by gamma as a common term. So, this is equal to 1 minus T4 minus T1 divided by pressure ratio to the power of gamma minus 1 by gamma can be taken as a common term, and inside the bracket. So, here you will get T4, here you will get T1. So, T4 minus T1, and these two will get cancelled. So, the air standard efficiency of the ideal Brayton cycle is 1 minus 1 by gamma. So, from the air standard efficiency of the ideal Brayton cycle, we can infer that it is a function of pressure ratio, which is P2 by P1. So, and also the gamma value, that is the specific heat ratio of an ideal working fluid. So, the thermal efficiency or the air standard efficiency depends upon the pressure ratio and the specific heat ratio. Okay. If any one of these two parameters changes, the efficiency of the Brayton cycle also changes. Now, to summarize the process of an ideal Brayton cycle, 1 to 2 is isentropic compression, 2 to 3 is constant pressure heat addition, 3 to 4 is isentropic expansion, and 4 to 1 is constant pressure heat rejection. This is the only process among the 4 air standard cycles which we have discussed, in which the heat rejection takes place at constant pressure, whereas in all the 3 previous air standard cycles, that is Otto cycle, diesel cycle and dual cycle, the heat rejection takes place at constant volume. So, how the actual cycle deviates from the ideal cycle? So, this is what this one, you can see here, the dotted line denotes the actual cycle. This is the actual cycle, this is the actual cycle, and this is the ideal cycle. This is the ideal cycle. So, you can see the dotted line which represents the actual cycle. There is a change in this portion, This, for example, if you take the ideal cycle, 1 to 2 is isentropic compression. This graph is plotted on a temperature entropy plot. 1 to 2 is isentropic compression, whereas in the actual case it is not isentropic. Similarly, from 1 to 2A is actual compression, 1 to 2A is actual compression, 1 to 2 is isentropic compression. Then from 2A to 3, you can see the shape of the curve is, it is not in exactly similar to the process 2 to 3. 2 to 3 is constant pressure heat addition. So, here also there is pressure drop or losses of heat, whatever it is, because the main reason for the actual cycle to deviate from the ideal cycle is due to the irreversibilities, losses due to friction, heat transfer, etc. These are all the primary reasons, major reasons. And 3 to 4 is isentropic expansion. In case of an ideal cycle, it is a line perpendicular to x-axis, whereas in case of a actual cycle, it is not isentropic expansion, it is deviating from the isentropic expansion process. Okay. And this is 4A, this is again 4A. Let me correct this one, because due to some system compatibility. So, QS is the amount of heat supplied during the process 2 to 3, and QR is the amount of heat rejected during the process 4 to 1. Okay. So, this is the in terms of the TS plot, how the actual cycle deviates from the ideal cycle. With this background, let us solve from numerical questions. Before that, in case of an actual gas turbine, normally what happens is it employs a open cycle, where the
air is admitted into the compressor, it is compressed, then the fuel is sprayed in the combustion chamber, and the products of combustion are expanded in the turbine, the power is produced, and the remaining gases are let out, the working fluid is let out to the atmosphere. So, it is not a closed cycle. There is the net work produced in the actual cycle, the net work done produced in the actual cycle is the difference between the turbine work and the compressor work, turbine work and the compressor work. In actual practice, 50 to 55% or even up to sometimes depends upon the isentropic efficiency of the turbine and compressor. At least 50% of the power produced by the turbine is used to drive the compressor. At least 50% of the power produced by the turbine is used to drive the compressor. There is a term called back work ratio. Back work ratio. So, it is the ratio of power required to drive the compressor, that is the work of compression divided by the power produced by the turbine, power produced by the turbine. This value will increase if the isentropic efficiency of the compressor and the turbine are less. In actual case, in real time practice, if the back work ratio of a gas turbine, this gas turbine engine is higher than a steam power plant. Generally, because the reason is, in case of a steam power plant or a thermal power plant, there we are pumping a liquid, we are not compressing a gas. In case of a gas turbine, a gas is compressed. So, because of that reason, the back work ratio of a steam power plant is much lesser than that of a gas turbine. In spite of this one, like more than 50% of the power which is produced by out of the power produced by the turbine, which is used to drive the compressor, this is the reason why it is employed. It has got a high power to weight ratio. It is a very small, it is a compact one, it is a compact device. So, it has got a high power to weight ratio. So, because of this reason, it is used in the applications, okay, in case of aircraft applications. So, these are some of the information which I would like to share. Now, let us solve some numerical questions. A gas turbine power plant operating on an ideal Brayton cycle has a pressure ratio of 8. Pressure ratio is given. The gas temperature is 27 degrees centigrade at the compressor inlet and 1027 at the turbine inlet. So, two temperatures are given, T1 and T3. Turbine compressor inlet is T1 and turbine inlet is, let us refer the diagram, turbine inlet, this is the turbine inlet, that is T3. Compressor inlet is T1, turbine inlet is T3. Determine the gas temperature at the exit of compressor and turbine, that is T2 and T4. Back work ratio is the ratio of the work of compression to the turbine work and the thermal efficiency. Okay. So, let us quickly solve this problem. So, let us write the given data. If the initial pressure is not given, we can assume it is 1 bar atmospheric condition. Okay, so P1 is 1 bar. Pressure ratio is given, P2 by P1 is equal to pressure ratio, that is equal to 8. So, P2 equal to 8 bar, P2 by P1, P2 by 1 is equal to 8, therefore, P2 equal to, so from this we can find P2 will be equal to P1 into Rp, so this is equal to 8 bar. T1 is equal to, what is the temperature at the 27 degrees centigrade? So, converted into Kelvin, 300 Kelvin, and T3 temperature of the working substance at the inlet of the turbine, 1027 I think, let me check the value, 1027, so converted into Kelvin, so this is in degrees centigrade, 1300 Kelvin, T3. So, using this relation T2 by T1 equal to P2 by P1 whole power gamma minus 1 by gamma, we can find the temperature at 2. Okay, so that's a, so process, consider the process 1 to 2, T2 by T1 is equal to pressure ratio to the power of gamma minus 1 by gamma. So, using this formula you can find T2. What is the value of T2? 543 Kelvin, 543
Kelvin, 543 Kelvin. So, the temperature at the end of compression, this is the, we are solving considering the ideal case. So, T1 is given, T3 is given, T2 is 543. So, here the temperature is 543. Let me plot the TS diagram, so that TS. So, 1 to 2, 2 to 3, 3 to 4 and 4 to 1. So, this is QR, this is QS. So, temperature here is 543 Kelvin, 543 Kelvin, T2 is equal to, here the temperature is T1 is equal to 300 Kelvin. So, after compression the temperature has raised. So, this is given as 1300 Kelvin, that is the maximum temperature in the cycle. Next we have to find out T4. For that consider the process 3 to 4, process 3 to 4. So, similarly use the same equation which we used for derivation, T3 by T4 is equal to P3 by P4 whole power gamma minus 1 by gamma. Okay, so, the same equation which I used for the derivation. See, T3 by T4 equal to P3 by P4 whole power gamma minus 1 by gamma, and replace P3 by P2, P3 by P2, because 2 to 3 is a constant pressure process. So, pressure at 3 will be equal to pressure at 2, and similarly 1 to 4 is a constant pressure, 4 to 1 is a constant pressure heat rejection process, P4 is equal to P1, this P2 by P1 will become pressure ratio Rp. So, gamma minus 1 by gamma. So, from this we can find T4, from this we can find T4 because T3 is given in the question. So, if you see the value of T4, 715 Kelvin, 715 Kelvin. If you see point 4, okay, actually when we initially mark, so it is slightly lower, but when we draw the actual diagram, it should be above 0.2 because T2 is 543 and T4 should be above. So, let me redraw this diagram. 1 to 2, 2 to 3, 3 to 4, 4 to 1. So, this is 4, this is 3. So, QS, QR. So, this will be 1. Now, if you mark the temperatures, T1 is given as 300 Kelvin, this is temperature, this is entropy, this is we have found as 543, T4 is coming here, T4 is coming here. So, this is 715 Kelvin and T3 is the highest temperature 1300 Kelvin. So, this is T1, this is T2, this is T4 and this is T3. So, you see the temperature is in the order, state point 1 is the lowest point, so it is 300, then 2 after compression the temperature 543, 4 should be above 0.2, 4 should be in this case 4 should be above 0.2 because T4 is 715 and T3 all the temperatures are in Kelvin. So, this is the exact representation of the TS. So, T4 should not, the 0.4 should not be lying below 0.2. Now, we have found T2 and T4. So, work of compression, the compressor work is Cp into T2 minus T1, turbine work is Cp into T3 minus T4. Okay, so I am using that one because we have been asked to find the back work ratio. Back work ratio is equal to work of compression to the turbine work. Okay, so this is work of compression is compression takes place during the process 1 to 2. Okay, so T2 minus T1. So, this formula you will be using Cp into T2 minus T1 for process 1 to 2 is compression and 3 to 4 is expansion and for this one. So, these two formulas I will be using Cp into T2 minus T1 divided by Cp into T3 minus T4. So, when we calculate WC, we are getting 244 kilojoule per kg, WT is 581, okay. So, 244 kilojoule per kg, turbine work is using this formula 581, and you substitute here 244 divided by 581, the back work ratio comes to around 0.42 or 42%, which is much higher compared to the back work ratio in case of a steam power plant, multiplied by 100. So, this is back work ratio BWR, back work ratio. So, the first question is gas temperature at the exit of compressor. At the exit of compressor is T2, at the exit of compressor is T2, that is exit of compressor is T2, and the turbine is T4, turbine is T4. And thermal efficiency of the cycle. So, thermal efficiency of the cycle, W net by heat supplied, W net by heat supplied. So, you can find QS is equal to both the heat addition and heat rejection at constant pressure. So, Cp into T3 minus T2, and QR is equal to Cp into T4 minus T1. So, what is the QS? QS is 417, this is 754 kilojoule per kg. All the values you know, once we know the 4 temperatures, we can find the QS, QR, W net, air standard efficiency. So, this is 754, this is 417 kilojoule per kg. Efficiency is equal to W net by QS. W net is QS minus QR, QS minus QR divided by QS. Substitute the value, you will get the efficiency around 45%, okay, 44.7%. The air standard efficiency of the ideal Brayton cycle can also be found using the formula which we derived, 1 minus 1 by pressure ratio power gamma minus 1 by gamma. So, you can use this formula also to find out 1 minus 1 by pressure ratio power gamma minus 1 by gamma. So, you can make a comparison of the answer that we are getting by the efficiency by using this formula, So, now let us quickly go to the next numerical question. Assuming I have taken the data whatever provided given in the first solved example. So, this is in continuation of that one. Assuming a compressor efficiency of 80% and turbine efficiency of 85%, the temperature of gas after compression and expansion are 320 and 490. Determine back work ratio and thermal efficiency of the actual cycle for the example 1, solved example 1, previous one. So, due to shortage of time, I am just would like to quickly run through it. So, the compressor efficiency is given as 80%, 0.8, turbine efficiency 85%, T2A and T4A, okay. So, this if you look at the actual cycle, this temperature is given T2A and T4A, that is the temperature of the working substance after compression is given is T2A, and T4A is the temperature after expansion. So, T2A is the temperature after compression in actual cycle, not ideal cycle, in actual cycle, and T4A is the temperature after expansion in actual cycle. So, this is actual, whereas T2 and T4 are the temperature after compression in ideal cycle. So, wherever I am using the notation A, that refers to actual T2A, T4A. If I am just writing T2 and T4, it is isentropic compression and isentropic expansion. Okay. Now I am going to find the actual work, actual work done by the turbine, actual power consumed by the compressor. So for the turbine work, if you want to find the turbine actual, already we have found the, for the ideal case, turbine work multiplied by the efficiency of the turbine, multiplied by the efficiency of the turbine. So efficiency, in the previous case we have got 581, in the previous case we have got 581. This is the turbine work which we have calculated. So this is equal to 581 into efficiency of the turbine is given as 85%. So that is 0.85, 0.85. So you will get the value 494 kilojoule per kg, 494. So everything we are calculating for 1 kg of the working fluid. Next, similarly we will find the compressor. See, when we are finding the turbine actual work, the efficiency to be multiplied. In case of compressor, it is a power consuming device, power absorbing device, not a power producing device. So the efficiency have to be divided. So compressor work divided by compressor efficiency. The compressor work which we got is 244 kilojoule per kg. So this is 244 kilojoule per kg divided by compressor efficiency is 80%. So divide by 0.8, divide by 0.8. So you will get 305 kilojoule per kg, 305 kilojoule per kg. Here you can see this is the ideal case, assuming the efficiency like 100%, but in actual the power consumed by the compressor is 305. Similarly, in case of a turbine, the power produced is 581 under ideal condition, but when we multiply by the actual efficiency of the turbine, the power produced comes down. So that is 494, 494. And if this efficiency drops further, the value of WC and WT obviously will again drop further. So that is what I have found here. So now you can find the back work ratio for the actual condition, compressor work of compression for the actual divided by actual. So this is equal to 62%. So the back work ratio increases 62%. Okay, so in case of ideal case, it is, in case of an ideal case, it is the back work ratio is 42%, but in case of actual, it has doubled, not double, it has halved, it has increased by half, about from 42 to 62%. Okay. So this is the BIS one, and similarly you can find the actual heat supplied, actual heat rejected. So actual heat supplied is, instead of, for the ideal condition we are using T3 minus T2, but for actual case we have to use heat supplied actual is equal to Cp into, instead of T3 minus T2 you have to put T2A, T2A, this is what you have to put, T2A. And similarly heat rejected actual is Cp into, okay, T4, this is the heat addition and this is the heat rejection. 2 to 3 is heat rejection, heat addition, 4 to 1 is heat rejection. So similarly here you have to take, instead of T4 you have to take T4A minus T1. So these two temperatures are given, you can find QS actual comes to 710 kilojoule per kg, 710 kilojoule per kg, and QRA is equal to 461 kilojoule per kg, 461.5 kilojoule per kg. So the net work produced will come down. So it is 249 kilojoule per kg, and the thermal efficiency is W net actual divided by heat supplied actual. So this comes, when you calculate, and using these two you can find W net actual, W net actual. So, you can find W net actual, this the efficiency comes from drops to 35%. So, let us compare the solved example 1 and 2. In case of a solved example 1, if you see the efficiency is 45%, the thermal efficiency of the Brayton cycle under ideal condition it is 45%, whereas in case of actual operating conditions where the efficiency of the compressor and turbine are given, it has dropped from 45% to 35%. The back work ratio in the previous example is 42%, whereas in this case it has increased to 62%. And similarly, there is a change in the heat supplied is 754, heat rejected is 417, and here if you see heat supplied is increased and heat rejection also increased. Net work done is 249 kilojoule per kg, whereas in this case it is 337. So, it has reduced from 337 to 249. As I said before, these values will drop further if the efficiency of the turbine and compressor is below 80 or 85%, whatever the number that are given for this example. And one more question is there, in a gas turbine hot combustion products with the specific heat Cp Cv is given, enters the turbine at 20 bar 1500 Kelvin and exits at 1 bar. The isentropic efficiency of the turbine is 94%. Determine the work developed by the turbine per kg of flow. This is 3 to 4 is actual, this is ideal, this is ideal process, and this is actual, So, 3 to 4 is isentropic expansion, 3 to 4A is actual expansion. So, the pressure is given P2 equal to P3 20 bar, P1 is this one. So, first we have to find out the value of gamma. Gamma is the ratio of Cp and Cv. So, you will get 1.2. Consider the process 3 to 4, first isentropic, T3 by T4 equal to this one. So, using this relation you can find T4, find the temperature T4. Now, the isentropic efficiency of the turbine is given, that is given as 94%, this value is given as 94%. Okay. So, the formula for the isentropic efficiency of the turbine is, it is the ratio of actual work by isentropic work. If the isentropic efficiency of the turbine is 100%, that means actual work is equal to isentropic work. Okay. So, using this formula I am finding T4A. Okay. This is required to find the actual power produced by the turbine. That is what has been asked in the question. Determine the work developed by the turbine. So, this is the WTA which we have to find out. So, the same formula which I used here, WT for the previous this one, and T4A, okay. T3 minus T4A, that is the actual work done by the turbine, actual power produced by the turbine or developed by the turbine. So, this is the answer. So, here you have to use the isentropic efficiency as this is the actual work, let me write WA. So, W net actual divided by W net isentropic. So, this is equal to, you can use this formula T3 minus T4A. This is the actual expansion, this is the ideal one. So, T3 minus T4A divided by T3 minus T4, and using this formula you can find T4A. Okay. So, T4A, so how much you are getting? 796 Kelvin. Okay. So, the actual turbine work will become Cp into, instead of T3 minus T4, if you write T3 minus T4, it is isentropic work, the work done by the turbine for an ideal case. So, if you have to write T3 minus T4A, so that comes 689.5 kg. So, to summarize, what we have discussed in this lecture number 10 is, we have compared the ideal Brayton cycle with the actual Brayton cycle. There is a deviation in the process from instead of 1 to 2, we have got 1 to 2a. It is not isentropic compression, and neither it is not isentropic expansion in case of ideal conditions. Then we have seen in case of an ideal Brayton cycle, the combustion process is replaced by a constant pressure heat addition process. Similarly, the exhaust process is replaced by a constant pressure heat rejection process. There is a new term which has been introduced, that is called back work ratio. It is the ratio of work of compression to work of the turbine work, the power produced by the turbine. So, with this, let me conclude the lecture number 10. Thank you.
Hi, my name is Lec10 and I teach sociology at IIT Kanpur. One of the things you must have noticed if you read or if you talk to people around you is that they often refer to something called globalization, or they often say we live in a global world. What does this mean? Today I'll tell you about how to think about globalization or interpret the word global in a sociological manner. When sociologists refer to globalization, they refer to three things. The first is that that it involves transplanetary processes, which means that something is going on across multiple borders, right? The second is that it involves heightened liquidity and interconnected flows. Now, by liquidity, and this is a term that was coined by the sociologist Zygmunt Bauman, we refer to the increasing interconnectedness of things across the globe, but we also refer to increasing instability across the world, which means that potentially something that is occurring many kilometers away from you actually influences the place that you live in. So, if there is a natural disaster happening in one part of the world, maybe that causes people to migrate from that area and they come and settle where you stay. So, that is what we mean by liquidity. And of course, when we are talking about liquidity, we are talking about things that are really moving from one place to the other. Now, the third aspect, and this is something that you may not conventionally come across in the way people use globalization, is that of structures. So, let's take an example. Supposing I, as an Indian citizen, wish to visit a foreign country. Let's say I want to go to South Africa. Can I just pick up my bags and hop on the next plane and go to South Africa? Any logical person is going to say, no, wait, you need to have documents such as your passport or visa. Now, this passport or this visa is a representation of the larger structure that governs how people move across borders. So, we have things like border control, national security agencies that consider what kind of people are going to move from one place to the other, correct? So, when we think about globalization, an average person typically tends to think about things moving or people moving from place to place. As sociologists, we also consider that there are structures that facilitate or direct this movement across multiple borders.